Today we're going to start talking about reactions in which the oxidation numbers of some of the reactants change when they become the products. In these reactions, we typically shorten oxidation and reduction to REDOX, or sometimes it's pronounced REDOX. And that's just short for reduction and oxidation. So let's talk about what reduction and oxidation mean. Oxidation means that the element loses electrons. And we know that when it loses electrons, it becomes more positive. With reduction, what happens is the element will gain electrons, and therefore it becomes more negative. So if we were to look at this number line, if the oxidation number were to be headed in this direction, becoming more positive, then it would be an oxidation reaction, where if it's becoming more negative, it would be a reduction reaction. These two things are always coupled together. One element will be oxidized and the other reduced. So when it's oxidized, it's going to lose electrons, and when it's reduced, it gains electrons. And that's how the two are coupled together. Now, it's kind of hard to make it work in your head that when something's reduced, it gains. So we use a mnemonic device to remind ourselves, and our mnemonic, and it works out really well because we're the Lockport Lions, is Leo says Gur. And what that means is when you lose electrons, it's oxidized. When it gains electrons, it's reduced. So hopefully that'll help you recall what oxidation and reduction is. All right, so when do we use this? Well, this happens in electrochemistry. Electrochemistry is when electricity is produced from chemical reactions. So we're going to start by talking about the simplest electrochemical reaction, which we call a single cell reaction. So this diagram that you're looking at, this is supposed to be a beaker, and it's filled with a solution. So there's a solution in here. This is a solid piece of metal, and this metal happens to be zinc. So that's a solid piece of zinc. Zinc, being a solid, has an oxidation number of 0. In our solution, I'm going to draw this so it looks more like a solution, we're going to have copper plus 2 ions. The copper plus 2 ions are the result of putting a copper salt in water. This could very likely be copper 2 chloride, which is a pretty blue color like you see here. So what's happening in a single cell reaction is a very simple reaction where you've actually seen it before. It's a single replacement reaction. I'm going to write out the full reaction so you can actually see what's happening. But I have zinc solid, which would have a 0 oxidation number, and I have copper 2 chloride. And then if you recall, we used table J to predict if this reaction would happen spontaneously. And what you'll find is that zinc is more reactive than copper. Copper is only the third one up from the bottom, and the other metals are all more reactive. So this reaction will occur, and what will happen is the copper will end up alone. It will have a 0 oxidation number, which implies that it's becoming a solid. And then the zinc will end up in the solution with the chlorine as a salt. Now, to show the oxidation and the reduction as separate reactions, we use something called a half reaction. And really what it does is it shows what happens to the electrons. And then also what happens to the oxidation numbers of the elements. For every redox reaction, there's going to be 2 half reactions. So you need to first identify which elements' oxidation numbers are changing. So you go back to your full reaction, which I have up here, and you're going to actually assign the oxidation numbers to all of the elements. Now, copper has more than one positive oxidation number, so in the copper 2 chloride, we're going to have to figure out chlorine's oxidation number to determine copper's. So chlorine being the last element in this compound, it has to be negative. The only negative oxidation number chlorine has is -1. Since there are 2 atoms of chlorine times the -1, the chlorine's charge is -2. So copper must be +2 in order for our compound to total 0. The same thing happens on the product side with the zinc chloride. Of course, zinc only has 1 positive oxidation number, so you could just record that as +2. So now we look at all of our oxidation numbers. Chlorine doesn't change from one side to the other. We call that a spectator ion, and we're going to leave that out of the half reactions when we write them. However, if you look, zinc is going from 0 to +2. So that's going to be one of our half reactions, and copper's going from +2 to 0. So that will be our other half reaction. So let's start writing that in. Typically what I do, because I can't easily fit this in my brain, that in reduction you have a gain of electrons, I put what it is on the reactant side first. So we have the zinc 0 and the copper +2. Then I leave kind of a space before I put in my reaction arrow, and you'll see why in a second. And then I'm going to go ahead and fill in what it becomes on the other side of the reaction. On the product side, zinc becomes zinc +2, and copper becomes copper 0. Now we're going to fill in our electrons in this reaction. So in order to do that, you need to understand that the charges have to be the same on both sides of the reaction. So we're going to be adding in electrons which are negative. So looking at our first half reaction, we have zinc 0 on one side and zinc +2 on the other. So right now the charge is higher on the product side than it is on the reactant side. Since electrons are negative and can only bring the charge down, we're going to put those electrons on the side of the reaction with a higher charge so it can bring that charge down to what it is on the other side. Since it was higher on the product side, I know that electrons are going to be one of my products, and the number of electrons is based on what the charge is on the other side. I have to get my charge down to 0 on my product side like it is on the reactant side. So I must have 2 electrons as my product. So now when we add up the charges, this side totals 0, and this side with the +2 and the -2 totals 0 as well. Now we're going to do the same thing for the copper. And I can tell you, I know it's already going to be on the reactant side, because if one element is losing electrons, the other must be gaining. But you could also look at the charges. This is +2, this is 0. The electrons go on the side of the reaction with a higher charge to bring it down to what it is on the other side. So we're going to actually need to gain 2 electrons, so that the charge on our reactant side, +2 and -2, totals 0, just like it is on our product side. So now we can actually assign which one is an oxidation half reaction and which one is a reduction half reaction. Going back to our mnemonic, if it loses electrons, it's oxidation. We see a loss of electrons when the electrons are a product, and that we see in our zinc half reaction. So this is oxidation. And then reduction, if you recall from our mnemonic, is a gain of electrons, which we see with copper, where the electrons are one of the reactants. So it's gaining those. So this is our reduction half reaction. And then to recall if it's spontaneous or not, we talked about this a little earlier on. You look in Table J, The way we've talked about it in the past, we said that if the single element, the one that's alone, is more reactive in table J, it will be spontaneous. Another way you can look at it, since now you know what that reaction would look like, if the solid metal, the zinc 0, is more reactive, then it will be spontaneous. Now we're going to look at a more complicated electrochemical reaction. Some people call this a two-cell reaction. Some people call this the voltaic cell because it is producing voltage. In this one, you're actually going to be creating electricity. Sometimes I've also heard it called galvanic or galvanic. I'm not really sure which it would be, but I like voltaic. It is the spontaneous production of electricity. We'll talk another day about the non-spontaneous version called the electrolytic. So there's a lot you have to do when you get this diagram. First, you need to recognize that this is a two-cell reaction, and you can do that because you see two beakers. You see this is called a salt bridge. You see a salt bridge, and you have two separate metals connected by a wire. And a lot of times in the middle of this wire is a clock or a voltmeter or something of that nature showing that electricity is going to be running through this wire that you have here and running some electronic device. So let's start labeling stuff. First of all, you can label this as the salt bridge. And essentially the salt bridge allows for a complete connection of the charges. It allows the charges to balance each other out because you're going to have electrons moving in one direction in this wire, and the charges need to finish balancing out or it'll run out very, very quickly. So that's our salt bridge. Now, in order to determine the flow of the electrons, you need to look in table J. So here's table J, and what you're going to do is you're going to try to find the most reactive metal between the two given in your diagram. So we have magnesium and we have copper. Copper's way down here and magnesium's up here. The more reactive metal, in this case magnesium, is going to lose electrons to the wire. So the electrons are actually going to flow out of the magnesium, these are electrons, and toward the copper electrode on the other side. Wherever those electrons are originating from will be the negative side of our battery, because that's really what this is. The other side is going to be our positive electrode. So when you're thinking of a battery that you might have in a device, this would be the negative end of that battery, and then this would be the positive end. Then to balance those charges, you're actually going to have a flow of ions, not electrons. Think of it this way. These are filled with a solution. These two beakers are filled with a solution. And this is also filled with a solution containing salt. Electrons can't swim. We're going to look at it that way. They can't swim. They can't go through water. We talked about that before. Water doesn't conduct. So it's not electrons that are flowing through here. Instead, it's ions that are flowing through this salt bridge in order to complete the connection and balance those charges. Now we can label our two electrodes. If you recall our mnemonic device from the front side, Leo says grr. We can use that to determine which side is losing electrons and which side is gaining. So looking back at our diagram, it's magnesium that's losing electrons to the wire. And over here at the copper electrode is where there will be a gain of electrons. So I'm going to actually label this Leo, and I'm going to label this grr. And then we're going to use an additional mnemonic device, which there's a place to record that way down at the bottom. And that is an ox gets small pox. The pox is really just there because it rhymes. And then red cat gets fat. And what this means is that the anode is where oxidation occurs, and that particular electrode will get smaller. Reduction occurs at the cathode, and that electrode is going to get bigger or fat. So let's go back up, and using this new mnemonic, not demonic, though it'll feel that way after a while, device, you're going to label your electrodes. So we decided over here is where there's a loss of electrons, and we said that that is oxidation. So using the mnemonic device for oxidation, anox, that means this is the anode. And what will actually happen as magnesium loses its electrons, it's going to become magnesium plus 2 and go into solution. So the concentration of magnesium plus 2 is going to increase as the size of this electrode decreases. On the other side, where we said there was a gain of electrons and therefore reduction is occurring, we're going to use the mnemonic device REDCat, reduction, red, cathode for cat. So this is the cathode where reduction is occurring. And actually what's happening here, it's kind of a strange situation. The copper plus 2 ions in the solution, that's actually what's going to be grabbing the electrons. And when it grabs those electrons, it's actually going to become copper solid. So what will happen is these ions will come out of solution and actually make this electrode thicker. It'll make it bigger over time. So let's look at the reaction that's actually occurring here. In this reaction, we have solid magnesium losing electrons and becoming magnesium in solution. The copper from the solution on this side is actually going to pick up electrons to become solid copper here. So the first thing we're going to do to determine the half reactions is first assign oxidation numbers. If an element is by itself, its oxidation number is always 0, so we can assign those to start with. When you look up copper, you're going to find that it has more than one positive oxidation number since it is a transition metal. So we're going to do it based on chlorine. Chlorine, again, when it's negative, is always -1. Since there are 2 atoms of chlorine, the total charge on chlorine is -2. So that means that copper must be +2 because the charge on this entire thing needs to total 0. On the other side, again, magnesium only has one positive oxidation number, it's +2, and chlorine would be -1. So now we're going to look through our reaction. You'll see that magnesium is going from 0 to +2, and copper is going from +2 to 0. So we're going to start writing down some little steps, little ideas on how to do this yourself when I'm not doing it with you. So the first thing that we just did was label the oxidation numbers. All right. The next thing we're going to do is we're going to look at all of the things that have changing oxidation numbers. So we kind of already identified magnesium is going from 0 to +2, and copper is going from +2 to 0. Chlorine isn't changing from one side to the other. We call that a spectator ion because there is no difference in it, and we're going to ignore that when we write our half reactions. So the second thing we are going to do is determine what changes. So we just decided that it was magnesium and it was copper that changed. We should be able to write our half reactions now for each of those. Remember, you're only dealing with one element when you write a half reaction. On the reactant side, magnesium is Mg0. I'm going to leave a little space and put the reaction arrow. And then on the product side, it's Mg +2. And then copper, I'm going to do the electrons when I'm done. Copper starts out as +2. And on the product side, it's 0. Just like on the front side, we're going to put the electrons on the side where the charge is higher because the electrons are going to lower the charge on that side of the reaction. So for magnesium, that means it's going to go on the product side, And I'm going to need 2 electrons in order to make it so that the total charge on this side is 0, just as it is on this side. For copper, however, since the charge is higher on the reactant side, I'm going to put my electrons on that side. And now its total charge on this side is 0, just as it is on this side. Now we should be able to say which one was oxidized and which one was reduced, again using Leo says Ger. Leo, lose electrons, oxidized. So we're going to look, which one do we lose electrons? Just like with heat, it's when the electrons are on the product side that they are lost. So this is our oxidation half reaction. And then using Ger, gain electrons reduction, it's a gain of electrons if it's on the reactant side, just like it was with heat. So this is our reduction half reaction. It's important that you're able to write these half reactions as we begin talking about balancing charge. In the past, we talked about the conservation of mass and energy in reactions. Now we're going to begin talking about how charge is conserved in a reaction when we talk about balancing redox reactions.